Now to rehash what we started at the very beginning, when we talked about the definition of energy at the very beginning, we said it was the ability to do work. We said it's a conserved quantity. We said that the total amount of energy that you have in a system always has to remain the same. You can change between different forms of energy, but it always has to equal each other. So now what we have is we have similar situations, but now we're going to look very specifically at kinetic energy and potential energy due to gravity, potential energy of elastic and work. You can set any of these two equations equal to each other if the situation warrants it. So for example, if I were to take a ball and take that ball and press it down on the spring, I would be doing work on the spring, and I can set that work equal to the elastic potential energy. If I were then to release the spring, the ball would leave the spring with a certain initial velocity. I could say that the elastic potential energy is equal to the kinetic energy that the ball has at that particular point. Or, halfway up, I could say that the elastic potential energy of the spring is equal to the kinetic energy at that point plus the potential energy that it has due to gravity. And once this ball gets to its highest point and it stops moving, I could say that the elastic potential energy at the bottom is equal to the gravitational potential energy that it has at the top. So depending on the situation, you can set multiple energies equal to each other. For example, if I have the potential energy due to gravity, right before something hits the ground, I can say all that potential energy has been converted into kinetic energy. So at this point, the potential energy at the top equals the kinetic energy at the bottom. So one of the biggest tricks that you have in your tool bag is trying to solve these questions is what two energies can I set equal to each other, and how can I make them cancel each other out? So you see this is the law of conservation of energy. This is how it's put on your formula chart, but really it's easier just to say what two energies can I set equal to each other, or what energy can I set equal to another two energies. It just says the kinetic energy that you have initially is plus the potential energy initially is equal to the kinetic energy final plus the potential energy final. Now remember, this potential energy could be due to elastic or it could be due to gravity. So you need to take that into account whenever you're doing these questions. So you see right here, they're all energies. We've talked about them all before. Initial just means at the beginning. So what is it to start with? Final means what is it when you end with? So in this particular example, it says a roller coaster begins at its highest hill of 100 meters above the surface of the earth. It says, what is the centripetal acceleration felt by the rider at point A? That point A was missing from the picture. But you want to know what the centripetal acceleration of the rider is at that particular point. Well, that's a kind of a review question. It says centripetal acceleration. Remember, centripetal acceleration requires that you know the velocity and the radius. And the radius is pretty easy to figure out. The radius in this case is going to be 20 meters, which is half the diameter of the loop. So really, the only thing that I need in order to solve this question is I need to know the velocity at point A. What I'm going to do is I'm going to look at it in terms of energy. My assumption is going to say that right here at the top of the roller coaster, the object has a velocity of 0. Okay, because it says it begins, it's starting there. So if it has a velocity of 0, that means it has a kinetic energy of 0. So all the energy at the beginning of this particular situation is going to be in terms of gravitational potential energy. Now, as I go down the roller coaster track, I'm going to hit a bottom point, and then I'm going to come back up. And when I get to this point right here, I have actually two types of energy. I have both gravitational potential energy, but I also have kinetic energy. And what I'm trying to do here is I'm trying to use this relationship of energy to solve for the velocity so I can turn around and solve for the centripetal acceleration. So what I want to do is I want to go ahead and substitute my values in here. So I have mass times gravity times initial height. I have mass times gravity times final height plus 1/2 mass velocity squared. Now, one of the nice things, and this is one of the things that trips people up the most, is they say, but I don't have the mass of the roller coaster. And if you look, the mass is present in every single variable. So it doesn't matter what the mass is, because you can divide by m and it makes no difference. That simplifies our equation just a little bit to the point where we get 9.8 times my initial height was 100 equals 9.8 times 40 plus 1/2 mv squared. So one of the nice things about this is you have these two terms, which are basically, they have the same 9.8 term and then the 140. So you can go ahead and multiply those out and then subtract. And when you do that, you end up getting a value of 588 equals 1/2 velocity squared. So now you would have to go and solve for the velocity. And when you do that, you multiply both sides by 2 to get rid of the half. Take the square root of both sides. And when you do that, you end up with a velocity of something like 34.3 meters per second. Now, a lot of people will make the mistake and say, there's my answer. But remember, we have right here what we were trying to solve for, centripetal acceleration. So we had to go and take this value and plug it in there. So we can now say that our final answer, the centripetal acceleration, is 34.3 squared divided by 20. When you multiply all that out, you end up getting a value of 58.8 meters per second squared. So just to put that in perspective, you would feel approximately 6 times heavier by going this velocity in this particular loop. So it's not very safe, because if you feel 6 times heavier at the top of the loop, it's going to be even worse at the bottom of the loop, and it would actually make it dangerous to the point where people would pass out. So not a fun roller coaster for you guys to actually ride. The next example says evaluate the validity of the experimental data shown below. And the key to this one is looking at this right here. Remember, mechanical energy is the sum of the kinetic and the potential energies. So when I look at the first data set, I say, okay, mechanical energy is the highest, and that's good, it's 10. And it's the sum of the kinetic, which is 4, and the gravitational potential energy, which is 6. And so that actually makes a lot of sense. This particular set of data is valid. When I look here, though, it says all this energy has been converted to gravitational potential energy, which is 10, and that the mechanical energy is actually dropped. Now remember, mechanical energy is basically what's conserved here. So the mechanical energy should have a value of 10 in order for the law of conservation of energy to be true. So we know this is an invalid set of data. Additionally, remember, the mechanical energy is the sum of the kinetic and the potential. You can't take 4 joules and 10 joules and get 6 joules. You can't just add them up and get that. It doesn't work that way. So because of that, there's 2 reasons why this is an invalid data set. The last example we have, it says 100 Newton per meter spring is compressed by a 0.25 meter by 2.25 meters, then released to fire a 0.4 kilogram ball vertically into the air. What is the maximum height the ball will reach? So we have 2 different types of energy here. You have the elastic energy and you have the gravitational potential energy. So what I want to do is I want to say that those 2 things are equal to each other. And the reason why I can do that is at the maximum height, velocity is 0. When the ball is pressed down on the spring, the velocity is 0. So even though there's kinetic energy in between the 2, the kinetic energy is not relevant for the 2 points that I'm actually looking at. So because of that, I can say potential energy due to gravity equals potential energy elastic. So now you can expand that equation out, and you can say mgh equals 1/2 k x squared. So you have k and x and m, and we're going to assume it's on Earth, so we have g, and we can go ahead and plug in and say 0.4 times 9.8 h equals 1/2 of 100 times 0.25 squared. Now, when you take 1/2 and multiply it by 100 and then by 0.25 squared, and you set it equal to 4 times, or excuse me, 0.4 times 9.8, you can actually go ahead and divide both sides by 0.4 times 9.8, and you can do this all at once. And when you do, you get a value of approximately, the height is 0.797 meters. Now make sure that you take into account that's a 0.4 kilogram ball. It didn't show up quite so well on some of those printouts, so make sure that you know it's a 0.4 kilogram ball.